Okay, so the next speaker is Manca from the University of Cagliari, and she will talk about a new Bayesian evidence measure for statistical hypothesis testing. Ms. Mara, the stage is yours.
Thank you for the introduction. I'm a third-year PhD student. As you said, I come from the University of Cagliari. Okay, my talk regards the definition of a Bayesian evidence measure that allows to perform Bayesian inference. Our work focused primarily on statistical hypothesis testing, that is a statistical inference method that allows to check the conformity of a given result with a certain hypothesis. While the problem of checking the conformity of a given result with a certain hypothesis in the frequentist framework have been extensively addressed, in the Bayesian one we have a few results. So our work is to construct an index that is as simple in the definition and in the usage, so in the computation, as the frequentist p-value. We defined such an index and we called it Bayesian Discrepancy Measure, so in short, BDM. Before defining the measure, in the univariate case, we have to recall which are the two statistical hypothesis testing approaches. So on one hand, we have the evaluative approach in which we fix only one hypothesis H and we test it. So this idea is based on Fisher's p-value, okay, that he introduced this measure in his theory of pure significance. Well, for the Bayesian field, we have the predicted p-values defined by Boxer, Rabin, Cagliari, and Berger. On the other hand, we have the comparative approach that I think is the most well-known approach, in which we have an null hypothesis H0 against an alternative hypothesis H1. So, for example, the Neyman-Pearson-Wald testing procedure follows this structure. For the Bayesian field, instead, we have the base factor and the full Bayesian significance test that was defined by Ferreira-Stern. This is the measure that is more similar to ours. Okay, now we start with the definition of the BDM in the univariate case. So in the Bayesian framework, so we have a posterior distribution G1 that is proportional to a prior distribution G0 and a likelihood function L. So what we would like to do is to test an hypothesis theta equal to theta h that is set by the researcher. So as I said before, we would like to check the conformity of the data, the conformity of a given result under a certain hypothesis. So in order to do this, we decided to compute the distance between the posterior median and the hypothesis. So we define the measure for the continuous case. So in this case, theta is scalar, but we can define the measure also when for the discrete case in analogous way. So we start with taking M1, that is the posterior median, and then we define IH, that is the discrepancy interval. So what is this interval? So for example, here, if we have that M1 is smaller than theta h, then the interval will be the interval between the posterior median M1 and the theta h. Then the measure, the BDM, is noted here with delta h, and is defined as 2 times the posterior probability in the interval IH, so in the discrepancy interval. So basically, we have to compute 2 times the integral of the posterior in the discrepancy interval. So we are computing here the volume, the area in this case, under the curve. Okay. We can also give an equivalent definition by means of the external interval. Okay. So here we have that in the case that we considered before, we will have theta h infinity. So the BDM will be 1 minus 2 the integral in the external interval. Okay. So here we are computing tail areas. Okay, instead of this. Okay. Then we can define this. We can formulate this definition in another way by considering the fact that the parameter space theta can be partitioned as theta a, theta h, and theta b. Okay, where theta a is this interval. Okay, theta h is the singleton, while theta b is this other interval, so the right hand side. Then the last definition can be written as 1 minus 2 the minimum posterior probability in theta a and theta b. Okay. We have to underline that this definition doesn't involve the computation of the posterior median, and this is good since if we want to generalize the BDM to the multivariate case, we cannot do that in an easy way by considering this definition, since in the multivariate case there is no unique definition of the posterior median, while here, so we avoid that computation, so we need to compute just tail areas. Okay, so we can see that the Bayesian discrepancy measure belongs to the interval 0,1, as the p-value does, since here we have that this posterior probability that we compute are in the interval 0, 1/2. Okay. So the Bayesian discrepancy measure has some properties. For example, it is invariant under one-to-one transformation of the parameter, and it also has the consistency property. So if the hypothesis is equal to the true value of the parameter, then the BDM follows a uniform distribution in the interval 0, 1, while otherwise we will have that the measure will converge to 1 in probability. Now we need to define a testing procedure. So we define the measure, now we define the testing procedure. So the Bayesian discrepancy test is a procedure that allows to reject the hypothesis when the measure is close to 1. Okay, so when h is far from the posterior median. So we would like to set some critical values, since here we are saying close to 1, but how much close to 1? So we suggest to set these critical values, 0.95, 0.99, and so on. And we fix these critical values by exploiting the fact that in some cases the relation between the p-value and the BDM is this one. So the p-value is the complement to 1 of the Bayesian discrepancy measure. So for the p-value we use the critical values like 0.05, 0.01. So here we will use the complement to 1. Of course, we have that this relation holds in those cases in which Bayesian conclusions are the same with equal to the frequentist one, and it happens with non-informative priors and particular models. Okay, now we can move on to the definition of the Bayesian discrepancy measure in the multivariate case. So for now we are not able to test all of the hypotheses. We get to test only the hypothesis that partition the parameter space. So we have to consider an hypothesis phi equal to phi h, where phi is the image of a non-function phi tilde, such that the transformation that goes from the starting parameter theta to phi zeta is bijective. Okay, so basically phi, okay, is the parameter of interest, since we want to test that, while zeta is the noise parameter. So we are going from theta to phi zeta. Okay. Then, if it's possible to compute the marginal posterior of the parameter of interest, then it's really easy to compute the BDM in the multivariate case, since we can compute the BDM by using the multivariate case methodology. So here, okay, we will use the posterior, the marginal posterior, okay? Otherwise, if we cannot do that because the marginal posterior cannot always be computed in an exact way, then we consider the fact that that kind of hypothesis that we saw before induces a partition of the parameter space theta. Okay, so this is the partition. So we have three sets of parameters in which the parameter of interest is equal, smaller or greater than pH. Then we can express the BDM as 1 minus 2 the minimum posterior probability in these two sets, theta A and theta B. So basically we are computing 1 minus 2 the minimum hypervolume under the hypersurface in these two sets. Okay. Now I know that it is a lot to take, so I have here an example that I hope it clarifies the definition. We have 50 IID observations that are distributed as a Weibull distribution. Okay, so we have that our sampling parameter theta is alpha lambda. We would like to test the hypothesis alpha equal to 2.5. So alpha is our parameter of interest, while lambda is the noise parameter. So the hypothesis identifies these three subsets. Okay. So this is the wall parameter space theta. Here I have theta A. The line is theta H, and theta B is this one on the right hand side. Then the posterior distribution, okay, by choosing a Jeffreys prior, it takes this form. So basically it is a surface on R3, and we can see its contour lines here, okay? So the BDM is 1 minus 2, the minimum probability in these two sets. So we can see that the minimum volume will be here, okay? So we have to, so this is the volume that we take. And then we get to the value, we have around 0.8. So in this case, if we fix a critical value of 0.95, then we cannot reject the hypothesis. We don't have enough evidence. Okay, so now we can move on to an application. In fact, thanks to the BDM, we constructed a general procedure that allows to compare parameter functions of two independent populations. This approach allows to tackle some problems that are not yet covered in the literature. In fact, for example, in the frequentist framework, it's hard to do this, since every time we need an ad hoc statistic in order to solve a specific problem, while this is a general procedure. Okay. In fact, we can take into account different distributions and different parameter transformation in the same way. So this is the procedure. So we consider two random variables, two prior densities G0L, and then we have two samples of IID observations. Then we get to two posterior density G1L, and then we indicate with theta the joint parameter vector of the two distributions. So theta 1 is the parameter vector of the first population, and theta 2 of the second population. Then we would like to test the hypothesis phi1 minus phi2 equal to 0, where phi-L is a function of the parameter. So, for example, this function can involve 2 or 3 components of the parameter, or just one component. It depends on the problem. Then the hypothesis induces a partition of the parameter space in this way. So we have phi1 that is smaller than phi2 equal or greater. Then to perform the test, okay, as we saw before, we have to compute the posterior probability in theta A and theta B. So here we need the joint posterior distribution that can be factorized in this way since we considered independent populations. So this is the procedure. Okay. So now we consider different distribution and different parameter transformation, such as we can compare skewness coefficients of two inverse Gaussian populations, variances of two gamma populations, but also two coefficients of variation of negative binomial populations. And we apply this methodology to a real data. Then, due to time limits, we will only see this third case, third example. Okay, we have that. The coefficient of variation is a measure of dispersion and is defined as the ratio between the standard deviation and the absolute value of the mean. Okay, so we assume a Jeffreys prior, and then we get to the posterior distribution that is known up to a normalizing constant. Okay, we don't need to know the exact form. Then we would like to test the hypothesis phi1 minus phi2 equal to 0, where phi L is the coefficient of variation. And again, we have that the hypothesis partition the space in this free set, but here we are visualizing only theta A and theta B since we need them to compute the posterior distribution. Then the posterior distribution is a four-dimensional integral that cannot be computed in an exact way. So we approximate it with this ratio by following the Monte Carlo integration method. We also apply the Metropolis-Hastings algorithm since, as I said before, we only know the posterior distribution up to a normalizing constant. Okay, so here we can see an example. So we wanted to model the number of new infections that were generated by an infectious subject. This kind of variable is right skewed and over dispersed, and then we can use the negative polynomial distribution in order to conduct this analysis. So here we consider two data sets. One is huge, and it contains the data tracing of two Indian states, while the other one is small, and it contains the cases from Hong Kong. So we cannot compare this data set by means of the mean of these two samples, since they have very different sizes. Then we decided to do that with the coefficient of variation. So we see that these ones are really close to each other. In fact, we get to a Bayesian discrepancy measure that is really small, and we said that we would like to reject the hypothesis when the measure is close to 1. So here we don't really have enough evidence in order to reject the hypothesis, so we cannot do that. Okay, now to summarize, we introduced a Bayesian test, a general procedure that allows to compare parameter functions of two independent populations. This procedure can be easily adapted to different problems. For now, we considered only sharp hypothesis, only hypothesis that can partition the parameter space, but the extension to more complex hypotheses is under study. So, for example, we would like to define a kind of Bayesian ANOVA. Then I'm applying also the BDM in a more general context, such as the use of the Bayesian discrepancy test for model selection in Gaussian graphical models. So here there are some references. That's it. Thank you.
So, if there are some questions from the audience? Yes. Okay, well, maybe I bring the microphone to you.
I don't do the microphone.
No, let me. Okay.
So my question is, have you use this CV for non-exponential families to test difference of parameters?
Yes,
Okay.
we use that, for example, for the skew normal distribution.
Okay.
Yeah.
Okay. Because just a suggestion. So since you are using the exponential family, so maybe you can work with the Jeffreys method. But another is, I think, suggested by Bargam and Bernard, where they use reference priors.
Okay.
So that is basically like maximizing the divergence, like the pullback divergence between the prior and the posterior distribution.
Yeah.
So it basically minimizes the influence of the prior, so on the data. So basically your data will go down.
Yeah.
So
Okay.
you can try that.
We like for now we are using the Jeffreys prior, but we can use any kind of prior, even like subjective priors.
Mhm.
Yeah.
Mhm.
Thank you.
Some other question?
I had more like a philosophical question I made at the beginning. I don't understand why in the Bayesian framework there is no like equivalent like p-value. I mean, is it because the parameters are already distribution or something like that?
Okay.
Or
Ok, vabbè, ora puoi metterla.
Okay.
Can you
Okay,
repeat
can you
it?
okay, yes, it's like why in the Bayesian framework there is no p-value equivalent?
No.
You said that and I was not sure.
Okay.
I understood
Okay, there are some attempts, like in the beginning. Here, in the Bayesian field, we have some attempts, okay? But you can apply this, but for example, in the conditional predictive p-value, these first two had some problems, like in a kind of philosophical way, since they use the data twice in the definition. Okay, so they received some critics, but then they then got to define the conditional predictive p-value that is really hard to be computed. I tried to do that, so and I didn't find any literature. Okay, after the 2000s. Okay, so I think it's a kind of good measure if you want to. Like in the theoretical way, but in the computational way, it's not really easy to use. Okay, so that's why we wanted to define a measure that is as simple as the p-value.
And so I have one question. You said that you are using this hypothesis testing, and in Bayesian methods there is the bias factor that is often used. And one of the properties that bias factor has is the so-called Occam-Razor property. So the easiest way in order to explain is the best one.
Yeah, like
also
the
this one, sorry?
Like the cheapest one.
Yeah, the cheapest one. So
Okay.
also your has this property, or?
Okay, the difference here is that we are, I forgot to say that when I was here. So here we are just testing the hypothesis H. So we are in the evaluative approach.
Okay, we are not comparing different.
Yes.
Okay,
Yeah,
so-
because here you have the alternative hypothesis, so you can say that, yeah.
Okay, okay. Thank you. So thank you again.